Good morning, everyone, and welcome once again to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with the country, and we recognize their valuable contributions to Australia and the global society. It's my great pleasure today to welcome Anna Chiquini. Okay, I got it right. Yeah. So Anna is joining us today to present on embracing uncertainties, why probabilistic mineral resource modeling matters. She's a chartered professional, a geologist with a diverse understanding of the mining industry, which she developed through work across various commodities and deposit types in the Americas and Asia Pacific. As a leader in geostatistical and resource modeling, Anna brings her expertise to the forefront of innovation with a master's degree in geostatistics from the University of Alberta in Canada. Anna has a robust background in mineral resource evaluation, disclosure, and management. Her passion lies in advancing best practices within the industry, and through her role, aims to push best practices in resource modeling forward and drive continuous improvement. So why don't you welcome me and everyone here? Join me in welcoming Anna to today's presentation. Thank you.
So thank you, Sustainable Minerals Institute, for having me here today. It's a great pleasure to speak on probabilistic mineral resource modeling. I'm quite passionate about this topic. Very happy to be here today. A little bit of the agenda that we're going to cover today. I'm going to start talking, introducing a little bit of my experience and my expertise. And then we're going to cover the current practice in resource modeling, some of the limitations of the current practice, learnings from other industries that we can leverage in mining, a proposed path forward, and some applications of that path forward. A little bit about me. I'm Anna Chiquini. I'm principal geologist with Geology AI. And I have a bachelor's degree in geology from the University of São Paulo in Brazil. A couple of years later, I did the citation program in applied geostatistics from the University of Alberta, and then moved on a couple of years later to a full master's degree in geostatistics and mining engineering from the same university. I have a couple of experience in a few deposits around the world. So in the Americas, in Central Asia, Kazakhstan, Mongolia, and here in Australia as well. I've always been working in the metals mining side of things, little bit of precious metals, gold and silver, and then some base metals as well. A couple of different deposit types, like copper porphyry, VMS deposits, and for both open pit and underground mines. Started my career longer than I care to admit now, 14 years ago, but as a resource geologist at Yamana Gold back home in Brazil. And then went through a couple of different companies, including Glencore Zinc based in Canada, and then more recently here in Rio Tinto Copper. So a little bit about the context that we're going to be speaking of today. So first thing, we're discussing the mining industry, of course. I thought it was important just to make that point to start with. And then we're going to be talking about the mineral resource modeling context and not the grade control. There are a couple of singularities between the approaches of the two contexts. So I wanted to make that clear as well. So we're talking about long-term resource models in a context where we have limited drilling data, right? So in the grade control side of things, we are We have a lot more data available. We have a dense data scenario. So that's not what we're going to be covered today. We're thinking of the resource modeling scenario where we have limited drilling data. So that covers project studies, for example. So concept study, pre-feasibility, and feasibility. It also is completely related to our reserves and how we report and public disclose our mineral resources and our reserves numbers to the market. Now let's talk a little bit on the current practice in resource modeling. In the mining industry, we tend to produce most of the time deterministic mineral resource models. And what do I mean by that? With deterministic, I mean that we have one geology interpretation, a single fixed grade estimation translating into one single block model. We normally use ordinary kriging or inverse distance to estimate the grades onto our block model. And yeah, we estimate the grades and also other properties for ore body characterization, like specific gravity or any geomet variables, for example. All of that gets translated into a block model. And that block model, of course, is built with a single fixed data set at a given point in time, right? So we go there, we drill, and then we produce one model using that data set. So it's the current practice is a very linear process that produces a single solution and a single result. So this is a simplified or a more generalistic version of what that linear process looks like nowadays. So as I said, we start by collecting the data here. So we go to a mineral deposit, we drill that mineral deposit at a given spacing, and then we go back to the drill holes, we sample those drill holes, we get then those samples and send to the lab. The lab is going to come back to us with some assay results and the grades for each one of those samples analyzed. We then get that data set and we start interpreting our ore body. So that interpretation can include lithology, mineralogy, structure, and many other aspects of geology. But that's the core of what we can get from the data. And then we move on to block modeling. So in block modeling, that's where we're going to translate all of those grade assays into estimated grades onto blocks. So in the block model, we translate both the grade estimation and any interpretation we've made with those data points. So that could be geology, again, the same things, lithology, mineralogy, and the structure, and also ore body characterization. And then we move on to resource classification, right? In resource classification, we have three main categories for resource. We have measured, indicated, and inferred resource. And as we move from inferred to measured, we're increasing the knowledge of the deposit. We're increasing probably the amount of data we have in given areas, and we become more certain of that material. With the resource classification on hand, we then go and apply some modifying factors to that block model, to that classified block model. And modifying factors, they're really any factor that can influence the extraction and the profitability of a mineral deposit. They could be mining modifying factors like the mining method, the access. They could be metallurgical modifying factors like the processing technique, recovery rates. They could be economic modifying factors, commodity prices, production costs, operation costs, or environmental, right? They could be availability of water. They could be land use, community concerns. So we apply all of that onto our classified mineral resource, and we translate that into categories of ore reserves. So we have two categories of ore reserves, proven and probable. And similar to measure, indicated, inferred, as we moved from probable to proven, we're increasing the level of uncertainty. Increasing the level of certainty. We're more sure of the proven ore reserve compared to the probable. finally, we then move on to reporting and public disclosure of those numbers. So that's governed by some reporting codes. Here in Australia, we of course have the JARC code. We also have the NI 43-101 in Canada and a couple of other reporting codes around the world. So this is just for an additional context of what the public disclosure looks like. This is all, of course, as the name says, public available information. So I've just took a screenshot of the annual reports from Glencore, Rio Tinto, and BHP here. But any company that's listed on the stock exchange has the obligation of disclosing their mineral resource and oil reserves number to the market. So this is what it looks like. We would have a set of average grades. We would have tonnage numbers, sometimes metal content, and separated by those categories of mineral resource and the equivalent categories of oil reserves. So anyone can go into the websites of the companies and look for their annual reports, and you should be able to see their reported numbers for the previous year. Now let's cover a little bit of the limitations of the current practice in resource modeling. The first limitation is nature itself, right? So nature is very uncertain. The mineral deposits are intrinsically deterministic, but they're unknown. They're intrinsically deterministic because there is one truth about the mineral deposit, right? It's not movable, it's not changeable. But we don't know what that truth is. And on top of that, geology is very variable at all scales. I came across this image this week, and I thought it was just a beautiful reminder of how much variable geology is, and in every possible scale, right? This could easily be a full outcrop of hundreds of meters long, but it's actually just a hand sample. But we're still able to interpret so many beautiful structures and movement. But yeah, if we had an outcrop of that, that's also the variability at a larger scale. So geology is really variable at all possible scales. The other limitation is related to the methods we're currently using for resource estimation. The most used estimation method nowadays in resource modeling is ordinary kriging, and followed by inverse distance. So Joyce Bazania and Jeff Poiver, they did a research in 2023 where they analyzed 150 reports, public reports from mineral resources. And they were able to see that almost half of the resource models that are reported to the industry now were built using ordinary kriging. And then a third of that, 33%, were built using inverse distance. So that those two are by far the most used techniques to estimate a resource model. Now, ordinary kriging is an optimal estimator. It was developed as an optimal estimator, but it's not optimal for long-term resource models. The estimates created from ordinary kriging, they're too smooth, and we're going to talk more about that in a second. And on top of that, we have something that's called the information effect. So the information effect reflects the fact that at the time of resource estimation, the data is limited. And we're going to talk more about the information effect as well. But those are the main limitations of the methods we're currently using in resource estimation. So the first one, ordinary kriging estimates are way too smooth, right? Ordinary kriging is designed to minimize estimation variance. So when we're developing and deriving the kriging equations, we're deriving that to minimize the estimation variance. So what ends up happening is that any extreme values, they can be low or high, they end up being evened out and kind of like averaged across your domains. And that leads to a much smoother distribution compared to the raw input data. And in the context of resource modeling, we try to control that degree of smoothing We're never going to be able to completely tackle the degree of smoothing, but we can try and minimize a little bit the degree of smoothing. And we do that by tuning some of the kriging parameters, some of the estimation parameters. We can do that by tuning the estimation search, trying restricting the estimation search a little bit, or considering multiple estimation passes. So here's an example of the effect that restricting the estimation search could have on the histograms of the estimated values. So for example, first of all, we have a quite large search. Here we're using 40 data points to estimate a single block. And that translates to a very smooth histogram. So the estimated values are quite squeezed around the mean. Now, if I decrease that to 10, that's when we start to see a little bit more of the tails of the histogram, the low and the high values. So our distribution of the estimated value are not as smooth. And then if I pick an extreme case, I'm utilizing only 5 data points to estimate a block, that's going to result in an even less, in an even smaller degree of smoothing. But then you start to get into all sorts of different problems. You start to get conditional bias, and your data doesn't really, your estimates don't have really, how can I say this? Yeah, they're not really correlated as they should, spatially. So estimation and ordinary kriging can be quite finicky to set up properly, right? Because there's so many different parameters you need to tune. You need to have a strategy to deal with extreme values as well and outliers. So yeah, it has all sorts of tradecraft that you need to tune properly to make sure you're balancing that degree of smoothing in your resource estimation. We as practitioners, we tend to be a little bit more comfortable with setting up an estimation workflow, but it's not necessarily that easy. Now let's discuss a little bit more of the information effect. So the information effect is the primary concern for long-term resource models. And as I've mentioned before, the data at the time of resource estimation is quite limited. Right, so we have a cartoon example of what that means. On the y-axis, we have the uncertainty. On the x-axis, we have the available information, so number of data per volume. And at the time of long-term resource model, we have quite a high degree of uncertainty. And as we move on time and acquire more information, at the time of mining, that degree of uncertainty is going to decrease. It is a fact because you're acquiring more information. So you're going to know more about your deposit. And that decrease in uncertainty from the time of resource modeling to the time of mining is called the information effect. But keep in mind, there's always going to be a level of remnant uncertainty that's never going to be fully resolved, even at the time of mining. Because there's always going to be a degree of uncertainty, even in the data that you're acquiring, but also you're never going to be able to sample your entire deposit, right? You're always drilling at a drilling grid. It can be a very tight drilling grid, like 5 or 10 meters, but you're never going to sample your entire volume. And this is an illustration of a real block model and how what's the effect of the information effect. On the left here, we have the block model at the time of resource modeling and mine planning. So we're estimating the grades onto the blocks here using that wide space drilling. And then as we move on time, at the time of mining, we have acquired a lot more information. And this context here is a context of grade control modeling and of an open pit deposit. So we have, I'm not sure if you, yeah, you can see. So you can see those tiny little points here. Each one of those points is a blast hole. So we have a very tight spacing there for data. at the time of mining, we are going to have that data available. And you can see how the estimate is quite different between those two scenarios, right? At the time of resource modeling, we use the drill holes to estimate those blocks, and we can't really see any of the structures. But as we get more information, we start to see a lot of complexity, and these beautiful structures here start popping up. And we can also see more pockets of higher grades, like here, and none of these we were able to see just with the wide space drilling data. So that's the information effect. It describes the fact that at the time of mining, there will always be, or there should be more information available to support the decision of mined material, to support the decision of destination for the mined material. So that's ultimately what we're trying to achieve in the context of the grade control. We're trying to define correctly what's the destination for that volume of material we are mining. Is that volume going to be sent to the mill? Is it going to be sent to a stockpile or to a waste dump? That's the type of decision that we're trying to make at the time of grade control modeling, which is not, as I said, the context that we're talking more about here today. So there's no other way around it. Uncertainty is really the state of the nature, right? Geological properties are highly variable at all scales, and the drilling at the time of resource modeling is relatively widely spaced. In some better cases, we can have drilling that's spaced by tens of meters, but we can have hundreds of meters apart as well. And those two factors combined are going to translate into a lot of uncertainty. So how do we deal with the uncertainty? That's the path forward that we're going to start discussing now. The good news is the global uncertainty can be quantified through geostatistical simulation. Now, the not so good news is that we know how to do that since the 1970s, really, but the uptake in mining has been limited so far. There are some perceived challenges and why the uptake has been a bit limited in mining. One of the challenges is the computational resources. When we first started doing geostatistical simulation, you can imagine the computers back in the 70s and 80s were not that powerful. So going through a geostatistical simulation workflow could be very intense on the computers that were available at that time. We have resolved that problem now, and that combined with some advances in the software space enables us to go through a geostatistical simulation workflow more easily. The other perceived challenge is the complexity of the workflows and upskilling of the workforce. As we've mentioned before, simulation, to be honest, it's not necessarily too much harder than conventional estimation, because conventional estimation has those tricky parameters you have to tune, but simulation is a lot more robust. It's a lot more robust to extreme values, extreme or outliers. They don't influence simulation that much as they influence an estimation workflow. It is also, you're not going to have the smoothing issue that you have with estimation. So simulation tends to be a lot more robust and not necessarily too much harder to set up than conventional estimation. And finally, we also feel, as human beings, we feel unease with the non-uniqueness of the results from a geostatistical simulation workflow, right? With a conventional estimation workflow, you end up with a single model. So you can perceive that as the truth. In the geostatistical simulation workflow, you would end up with hundreds of scenarios. And each and every one of those scenarios, they have the same probability of being the truth. So then what do you do with all of that in hand, right? So that's, we tend to feel a bit unease about having so many possibilities. There are a couple of other industries that we can really learn from. And one of them is the climate and meteorology industry. So the numerical climate models, they can simulate the interactions of important drivers of climate, like the atmosphere, oceans, land surface, and ice. For anyone who was in Brisbane last week or in Southeast Queensland, is very much aware of how important climate and meteorology prediction is. So Alfred made sure we remember about that. The other industry that uses simulation quite extensively is the finance industry, for financial and risk modeling, to predict asset prices, market movements. And finally, hydrogeology also uses simulation for groundwater modeling to predict things like porosity, conductivity, and contaminant transport. Now, the industry that we can for sure leverage a lot of knowledge, and it's directly applicable to mining, is the oil and gas industry. In oil and gas, they have a really big issue of limited data. So their wells can be spaced by hundreds or kilometers apart. And we're actually a bit spoiled in mining on the amount of data we get sometimes compared to the oil and gas industry. So they need to understand uncertainty properly. There's no way around for them. Building a well is extremely expensive, so they need to know what is the optimal location to build that well and what's the amount of uncertainty they have on all of their estimates. So they're very comfortable with dealing with uncertainty and processing that uncertainty and using a geostatistical simulation workflow. So here's a proposed framework for geostatistical simulation, how we can start quantifying that uncertainty. First of all, we're talking about a geostatistical simulation framework and large-scale uncertainty. So we start with, this is of course a cartoon illustration of what the geostatistical simulation framework can look like. We start with some prior parameters on the left side here. By prior parameters, I mean the grade distribution, the proportion of categorical variables, for example, your variogram. Those are not going to change, right? Those are fixed. And then we move on and we can create realizations of our data. So instead of having one fixed data histogram, we can input that through a data realization framework. And then we move on to the geological model. So we can simulate and generate scenarios of the boundaries of our geology, of our rock types and geology domains. And finally, those two can be combined into a block model, combining the realizations of your geology volumes and the geology domains. And that is going to translate to L realizations. We usually do 100 in mining. That seems to be a magic number, but there are people who advocate for having more realizations to have more stable results. Typically, we still do 100. And so, yeah, the end goal of that is generating, let's say, 100 realizations of your grade estimates, of your geology, any other ore body characterization property that you wish to simulate. And this is an example of a real workflow that was done. On the left side, we have the prior parameters. Is it too small? Yeah, so we start with the prior parameters. So first of all, we're going to have a data set, so a data histogram, and then we're going to have a variogram for that deposit as well. And this is a visualization of our data, of our drilling data, and the domains that have been modeled, deterministic domains that have been modeled using that data. And then we go ahead and we create realizations of that data. We have in green our real data histogram, and underlaid there in gray we have the realizations of that data. Those are, of course, going to be quite close to our real data histogram. We then move on to having realizations of the geological model. So we can see that I'm representing here two realizations of the geological model. And we can see, for example, in the bottom here, on the second realization, we have a little pocket of the low grade and high grade domain that did not show up in the first realization. So that illustrates a bit of the uncertainty that we can expect to see going through a geostatistical simulation framework. And then finally, we create grade realizations within those geology domains. So similarly, we can see that there are some pockets of higher grades that appeared here in the top in the first realization that we cannot see on the second realization. And we repeat that, as I said, 100 times. So we create 100 of different scenarios for the geology model, the data, the data distribution histogram, and the grade realizations. Now, what can we do with those results, right? The results, they can be utilized on a local or block by block basis, but also on a global basis. And what do I mean by that? First of all, you can create a lot of different types of summaries with those results. The first thing and the more natural thing you can do is to create a probability of a block of belonging to a specific domain. So that's what I'm showing here. And the top, I'm showing the probability of each block to belong to the low-grade domain, as you can see here in the y-axis. So we can see that in the blocks that belong to the center of the domain, we have 100% of probability of that little block being inside the low-grade domain. So we're very certain that those blocks will belong to the low-grade domain. On the other hand, as we move away from the center of the mineralization, we can see that the solid blue here, we have a 0% chance that those blocks are going to be inside the low-grade mineralization. So they likely belong to the waste or the background domain. And the bottom, it's this an equivalent image for the high-grade domain. And then here, I'm summarizing results of a categorical simulation for a single vein using something that's called the entropy. Finally, on a global basis, I can calculate resources for all of those realizations. And instead of having one fixed number for my average grade, for my tonnage and metal content, I'm going to have a distribution of possible values. So in this example, I can see that my deposit can vary from, a little over 400 kilo ounces of metal content, all the way up to more than 550,000 ounces of metal content. Oh, sorry. So there are a couple of key parameters that really influence the resources. The first one for sure is the geology boundaries, the limits, and the surfaces, so your geology model. The second one, depending on the deposit type, is the thickness. So thickness can be, can influence a lot vein type deposits, and the proportions of categorical variables, and also the histograms of the grades of the continuous variables. The current practice in geostatistical simulation usually is simulating only the grade values and not so much the geology domains and the structures. So that would be, we would be creating multiple realizations of a single set of fixed input parameters. So with a single geology model, a single structural model, we're just simulating the grades. But by doing that, we're not really tackling the full spectrum of uncertainty that we can have in a resource model. So it's really essential to include realizations of the structural framework, the geological model, all of the input modeling parameters, and the data. Now, again, what can we do with those results from a geostatistical simulation framework? There are a couple of important and different applications of that. The first one is in drill hole spacing studies. So drill hole spacing studies are a natural progression of a geostatistical simulation workflow. And they can strongly support your mineral resource classification because you're measuring the uncertainty and the risk that is associated with certain drilling spacings. So that's an example here. I can see how much my uncertainty is decreasing as we move from wide space drilling of 200 meters towards a tighter space drilling of 50 meters. So our uncertainty is decreasing. And I can associate that with my categories of mineral resource, of measured, indicated, and inferred, and strongly support my classification basis. I can also use the geostatistical simulation results to produce stochastic mine planning. The other current practice in the industry is creating one single mine plan and hoping that's going to be the correct one and the closer to the truth. That's not possible. We need to use all simulated realizations for mine planning as well. And that honestly has been one of the holdups in mining of why geostatistical simulation frameworks are not that adopted still in mining, because we end up stopping in the mine planning stage, and the results from the geostatistical simulation workflow is not really translated into mine planning. So by applying all of the realizations into a more stochastic mine planning scenario, we can make the most out of those results for sure. So that would allow us to consider a position on risk when we are choosing our optimal pit scenario. Here's an example of a stochastic mine plan case study where we generated a deterministic plan based on a single estimated model, and we generated many different scenarios, but we're showing here just 3 of them. We're showing the most risky option, a more conservative option, and a mid-level approach. And this is how that would translate onto economics, right? So in summary, I'm plotting here my deterministic optimal pit, and this is my position on risk, and this is the expected value of my pit. So what I'm clearly seeing here is that for the same position on risk, I could actually be picking an optimal pit that would generate a lot more value. So that's how much we're missing by not using stochastic mine planning. And finally, of course, a very big application of a geostatistical simulation framework is in mineral resources reporting. So we should also be using all of the simulated realizations to calculate the mineral resource numbers. As I've mentioned previously, we would end up with a distribution of a mineral resource numbers, and we could then go and report the expected value, so the mean value of that distribution as the final reported numbers to the market. But the really important thing here is that the uncertainty can be assessed for any number you decide to report onto, right? You can have measures of uncertainty and what's the probability of that number occurring for any number that you decide to report on. Yeah, so finally, let's embrace uncertainty. Nature is uncertain. We have limited data, and reporting with multiple realizations should be as easy as with one single estimated model. If we must, we can get a single model as well, but we shouldn't provide any reason to maintain one single model for mineral resources or mine planning. We should be processing all of the realizations through the complete workflow. And yeah, that's it. Thank you.
Thank you very much, Anna. Okay, any questions?
Thank you, Anna. Good morning, and thank you very much for a fascinating talk. I certainly learned a lot. Uncertainty is the theme. Where are we, and I'm asking this from this is not my field, so maybe this has been done already. Where are we from introducing another layer on top of this? You've got good data, and it's numbers going in and numbers coming out of a machine. But somewhere there must be interpretation, and the interpretation would be from a geologist who knows his stuff, knows stratigraphy, and he knows, and experience as well, which I don't know if you still get those guys. Maybe you do. I remember that. No, I'm talking to the younger generations. I'm reminded of, a geologist on a mine getting a phone call in the middle of the night from a frantic mine captain underground saying, "We lost the reef." And he would go down without any information, any numbers, any data, and he would look around and say, "Your reef is in the roof, 3 meters up." So that sort of knowledge, and again, I don't know if it's being done, it's not my field, but is there a possibility of putting another layer on top of that where you can, through AI possibly, replace the knowledge and the experience of a trained geologist? And sorry for stepping on the toes.
Thanks for the question. Yeah, that's a great question. And we do, absolutely. So in this framework here, one of the inputs in that framework would be the interpretation from the geologist. And we would be varying that interpretation is likely, but that would be one of the inputs into the framework. Yeah. Yes, exactly. Yeah. Mm-hmm.
Yeah. Thanks, Anna. I guess just one observation and then a question, if you don't mind. So the other benefit from this work is to work backwards and say, well, how much data do I need to get a certain level of confidence in my estimate? So you can use this information to backwardly calculate your sampling regime to help inform a desired level of confidence. So just another, I don't think you raised that one. Anna, this is obviously really applicable to data that is additive from an estimation point of view. And I guess a lot of the data we work with here is geometallurgical, metallurgical data or geotechnical data, which is not necessarily additive, and therefore some of these estimation methods are not necessarily applicable or as applicable to those methods. So a little beyond your presentation, but are you aware of applications to those other types of data and whether variations of this methodology are equally applicable?
Mm-hmm. Yeah. So in the geomatch space, you could definitely apply, for example, machine learning techniques to get regressions between the variables, but apply that onto the results from a geostatistical simulation framework. With geotech is more difficult, right? Because geotech can be, the geotech data and parameters can be quite influenced by the direction of drilling that you have. So it's quite, they're not additive variables either. So it's quite tricky. Yeah, so we haven't done a lot of work on the geotech space just yet.
Yes, and my question sort of follows on from that. There are a couple of slides later with the drilling section. Keep going. Yep, keep going, keep going, keep going. Yes, there. So one comment as a structural geologist is that I don't see much in the way of uncertainty applied to constant orientation of drilling. Because if you took a model for all of those orientations, then the preferential orientation of fractures and veins that you see is perpendicular to that. So everybody draws the stereo net on the basis of all that drilling. And the issue is that if there was a whole lot of north-south fractures in that imagery, that's not even taken into account by that modelling. It's only a fluke if you see it. And I would really like to see some of this uncertainty starting to be applied properly to this sort of stuff, because we really need to see holes that are at 90 degrees to that to help measure the uncertainty, both in the geotechnical area and especially in the gold world with veining. And it's a continuing problem in our business, especially when, in our case here, it's sort of east-west. And I don't know what you've thought about in the world of stereo nets and uncertainty, but it's something we really need to get into.
100%, yes, it is. Yeah, as I was just saying with geotech, it's really difficult because all of the parameters are so sensitive to the direction of drilling, right? So if you drill in one direction, you're going to get potentially completely different results from drilling in the other direction, and how much we're drilling. Yeah, so geotech can be quite complex in that sense, for sure.
Thanks, Anna. That was fascinating. I've got written down a whole bunch of questions that came up during there, but I'll only annoy you with one. Just to go on from what Quentin was saying and to preface the question, the geological modelling is often has far more consequence to the final metal grade than the choices that you make in the resource estimation space. And if that's not the case, then you probably need to do a lot more geological modelling, but that's one of the questions when you're building a geological model for a resource estimation is what scale do you go down to? Like how smaller domains do you end up making? And, at present, that is just it's a vibe by the geologist that's doing it. You kind of go, well, this one looks kind of big enough. I mean, as far as I understand, maybe things have moved on a bit, but do you think there's a way that we can look at the drill data, look at the data we have and sort of determine what an optimal size and scale to be building these geological models at, doing these hard boundary domains, and then, and that will then guide further drill spacing in our resource drill out and that sort of thing. Do you think there's a scope, a possibility to do that with some sort of AI machine learning type approach looking at the data?
I wouldn't be able to comment on the AI and machine learning because I'm not specialized in that area. But scale is definitely a big component of the whole simulation framework as well.
Yeah.
So we simulate at a point scale, so a very, very tiny little scale, and then we upscale that to a mining scale, right? So what is going to be your selective mining unit? Yeah. So that's usually the scale we tend to work with for final results into resource reporting and mine planning. But going down onto the modeling scale and understanding what's the scale that you actually have to build your geology model on, that comes down to the knowledge of each deposit, right? There is no blanket rule for it. Yeah.
Nick wants to say something. Thanks, Anna. It's a leading question. As you know, I work in the industry for many years, and as you said, simulation's been around since 1970s, and the tools have never been around to do it efficiently and effectively. So maybe it's a leading question to kind of go down the path of what tools you recommend with respect to doing this moving forward.
Yeah, there are a couple of quite powerful software tools out there. Now I'm in a bit of a pickle here. Yeah, so the company I work for has one of those software packages. It's called the RMSP. And yeah, you can go and look it up, and it is quite efficient, and it can process simulation results in a quite an efficient manner. But yeah, so look it up. Thanks, just.
So just to close out, so a simulation in the past, one of the restrictions was that the time to do it for an experienced resource estimator was quite significant compared to running a more
From my experience now, we would try to compare with time frames to do detailed simulation studies as the data estimate.
We've got a number of questions online, and we'll probably read one or two of them. So one from Andy Reynolds asked, can geostatistics simulations provide different realizations of the location of bounding faces of a narrow vein deposit? And then he followed up with, could reporting codes do more to encourage use of probabilistic methods?
Yeah, so on the first question, yes, we can. One of the results we can produce are definitely the location of a vein in a vein pipe deposit. And on the second question, as of now, there isn't really anything that encourages us to go through an uncertainty assessment workflow in the reporting codes. There's nothing explicitly telling us that we should be quantifying uncertainty in the reporting codes. So yeah, that could be something that as a community we can discuss for sure.
I'll read another one from Tim. Tim Napierman says, great talk, Anna, and thanks. How do you teach the senior decision makers to interpret the uncertainties that you can provide?
Sorry, can you say that again?
How do you teach senior decision makers to interpret the uncertainties that you can provide?
Yeah, the communication of those results can definitely be a challenge. So you need to, I find that with senior management, you need to translate that into dollar value, right? So how much how many dollars you could be saving or you could be spending depending on the type of decision you make. So I find that in general, that can be an efficient way of communicating those results.
Hi, Anna. Yep, great talk. I really enjoyed that. So thank you for coming out here today and giving that. I guess I wanted to touch a bit on your current role. I mean, you've had quite an interesting career. Pivoting towards a company that you're working with right now with lots of new technologies that are being developed globally, sort of to help improve that early stage characterization of ore deposits. I guess in the context of your talk today, like what do you see as being kind of the data integration or the opportunities we have with all of those new data sets?
Yeah, I think one of the biggest opportunities is, well, two things actually. The first one is enabling that workflow, right? Making it easier for us to jump onto really adopting those type of workflows. And then the second one is making that in an efficient manner, in a way that you can really iterate over your results and feed more input data in a very smooth and natural manner, right? As opposed to having that really linear process that is just a chunk of work that needs to get repeated all the way again in chunks of works at given points in time. So having something that's more dynamic and integrated across that value chain is something that is really a big opportunity for us in mind.
Thank you very much. I thought, Anna, perhaps useful to discuss, I guess, how the models are consumed and used down the line. So the next stage being mine planning, scheduling, because my understanding, like while simulation and the methodology has been around for many years, it's the ability of the engineers to use that in mine planning, scheduling efficiently, effectively, and in good time. That has been a big limitation in its adoption, is its usability by the people down the line, which then leads to the financial forecasting as well.
100%. Yeah, I completely agree. That has been a limitation. So we, as geologists and geostatisticians, we produce the geostatistical simulation, we get those hundreds of scenarios, and then mine planners cannot use it, right? So it ends up dying, and then there's no big push from the consumers for us to really adopt that framework as just a normal practice, as standard practice. Now, there are a couple of tools in the market now that are doing stochastic mine planning commercially. And when we are able to adopt that end term of the spectrum, that is really going to feed back onto us as geologists and geostatisticians to adopt the geostatistical simulation framework as standard practice. So yeah, we really should be processing all of the simulated realizations all the way to mine planning, and getting, instead of getting just one single optimal pit, getting that uncertainty on the optimal pit and mine plans as well.
Going back to geologists versus engineers and mineral processing, I mean, one issue we do have, I believe, and Mark and various other people probably support this, is that the geological world of resource estimation usually ends up at double what the reserve and mine material is, and we need to get much better at not being so diluted as the process continues. I suppose the question from that is, in that uncertainty domain between the two, where do you see the biggest faults as to why that resource to reserve transformation is, say, 50% for the worst of them?
Well, first of all, in the way we're currently doing things, we don't get the spectrum of results, right? We get one single resource model that's very smoothed, and we don't know how much that can vary. But if we went through a simulation workflow, we would know that those results could actually could range from, I don't know, X to Z. And then we would be able to see, okay, so how much my reserve can be, and you would get a much more integrated view of the possibilities you have with that mineral deposit. And that's going to guide you in your decision-making going forward.
Perhaps the last one from online, from Bruno Fonseca, is asking, from your experience, what would be the biggest barrier to stopping probabilistic modeling from becoming a normal thing, a common thing?
If I had to choose one, well, the three main limitations or perceived challenges are definitely these three: computational resources, complexity of the workflows, and just learning how to deal with the non-uniqueness of the results. I think, to me, the last one is the biggest hurdle we still face. Explaining why the results are non-unique, because it has such a strong psychological effect and human aspect to it. So I think conveying that message in the proper way, for me, is the biggest challenge that we face.
Thank you very much, Anna. I think that'll be all for today. We're quite sorry to the guys online. We realize there's a number of questions, so kindly forward out to Anna. We'll help you with that process, and maybe Anna could provide answers to them. Next week, hopefully, I would want to see your faces once again. And we'll be having Evelyn Mervyn from Anglo American talking to us about the importance of accounting for carbon emissions from deforestation at mine sites, which is quite another important topic when it comes to mine decarbonization. So let's give it once again to Anna for joining us today. And thanks for coming.